In the previous section, I introduced the principle of slice selection and frequency encoding with gradient switching, and I said this is almost the essential, the basic imaging sequence. What I haven't told you is how do we get the second spatial dimension encoded. So let's recap what we've seen. We have had an RF pulse that flips the magnetization to transverse plane by alpha degrees. We have the slice select gradient with the rephase, I will not comment on here. The frequency encode with echo formation. This is the condition of zero integral for the gradient, so this defines the echo time, TE. This is the signal that is produced. The data sampling is done over this time period, and this is what is the sample signal that arrives in our computer. Now what we see here is that this produces us a slice selection, that's what this does, and an encoding of a projection in one direction. But where's the second dimension? So for the second dimension, we turn on the phase encode gradient here along Y. We just turn on the gradient at this position for a certain amount of time with a certain amplitude. And this is now the entire experiment. However, this gradient is applied, this phase encode gradient is applied with a certain amplitude. That does not give us spatial information. So this is repeated with a changed amplitude, so here reduced by an amount delta gy. And we repeat it again. We repeat it every tr seconds, that's the repetition time. We increment or decrement by delta gy, and so forth. We go through 0, we go into the negative values, and so forth, until we have scanned the number of phase encode steps that we want. So what we have here now is three gradients. The slice selection gradient, perpendicular read gradient, and the phase encode is perpendicular to both slice and read. This gives us a Cartesian encoding of the signal. So we are distinguishing three phases of the imaging sequence. We have, first part is excitation. Since all the spatial manipulations, spatial encoding is done on the transverse plane, we need to get the magnetization into the transverse plane. During excitation, we typically there is slice selection that's being done. The next phase is phase encoding, so that is the encoding of the second dimension, and then we have frequency or encoding and echo formation, that is the encoding of the first spatial dimension. So we have slice selection, frequency encoding, and phase encoding, all this together, repeated every tr second with the phase encode gradient changing after every RF pulse. This gives us the information to generate an image. Now, to understand how this phase encode gradient produces the information that allows us to reconstruct an image is not trivial, and I'm going to try in the next following slides try to explain this. It is difficult to understand how this phase encoding gradient allows to encode the second spatial dimension. So, and that's exactly the question we're going to look at now. So let's say we have a two-dimensional object along X and Y. We're looking at the voxel magnetization, the transverse voxel magnetization in our two-dimensional object. It's a 7x7 object here. Now, if we do apply a phase encode gradient along Y, then we apply it for a certain duration with a certain amplitude, then we have along Y, we have phases that change. For all the positions along X, they have the same position, so they have the same phase, but along Y, this depends on their position in Y. These guys have not changed, the others have changed. These turn to the right, and these turn to the left on the below. Now we'll repeat this with twice the gradient strength. So this means that if we repeat this experiment with twice the gradient strength, for each of the positions, the vector move by twice the angle. Now we'll say we have applied this gradient for time tau, and we'll express this in imaginary and real compositions in the complex plane. So we'll say the X magnetization is real and the Y magnetization is imaginary. These X and Y's That's in magnetization space. This is the real space that pertains to here. So if we look at a given voxel, then its position, its phase is given by the position along y, the duration tau, and the gradient gy. So the phase here is given by this term here. That's what's happened after applying this gradient gy for a duration tau. Now after what we have applied this phase encode gradient, gy for tau seconds, we have this phase term here. I'll rewrite this here. This is the situation that we have. And now we want to look at what happens with during the application of the readout gradient. And here we're not going to deal with the complexities of the need to generate an echo. We'll just start at what's happening at the time of the echo. So at the time of echo, we will start with a phase evolution that's determined now because it's under the influence of an x gradient. That's determined by the magnitude of the gradient, the position, and the time variable tau. So I'll plot this, and as the gradient is turned on along x, then we will see now that the magnetizations along y, they have the same precessional frequency here, but along x the precessional frequency is different. These turn counterclockwise, these turn clockwise, these turn counterclockwise, and here on resonance they don't move, they just have the phase difference that was induced by the y gradient. So clearly, if we now Fourier transform this signal, this is what we're observing here, we will get the different frequencies as a function of x position. We'll now take these two terms here and we'll rewrite them. And we'll rewrite them such that we introduce the variables kx, ky here, the Fourier pair variables to x and y to the position. So, and this we can write as e to the kx x plus kyy times I. That's the rewriting here. We have used here the definition for the k-space vector in this case. So that's the phase of our voxel magnetization that we have for a position x and y that is given. Okay, so we have seen that applying a gradient for a short time along y in the phase encode direction produces a phase twist according to the position in y. And then applying the gradient along x induces precessional frequencies that are being recorded that depend on the position in y. And now, how can we understand how this generates the necessary information for image reconstruction? What we're now going to do is we're going to look at the phase of a single pixel in the xy plane. Okay, we'll take the magnetization phase of a single pixel at a given position. Say you can consider it a pointwise object, a capillary or something, just a pointwise object, idealized with no dimensions. We'll just take a single pixel. And we'll plot on the horizontal axis here, we will plot the time. During that time, we have the readout, that is the gradient gx is on. So we have gx times t is the phase is dependent on gx times t. So we'll start out here. We apply the gradient along x, and we will have, over time, as we apply the gradient, we have the phase of our magnetization that changes with time. This is simple precession, the phase increments for this particular voxel. Remember, we're just looking at one single voxel, one single pixel in space. We're just considering that case. And so now we have the evolution of the phase with time. That's basically a representation of precession. So we can say we are digitizing here 7 time points. We're looking at 7 time points. Now we'll do step 1. We will apply a gradient along y. That gradient will induce a phase twist according to the position of the voxel. So after having applied this gradient, the magnetization of our voxel starts out at this position. And now during the time when we apply the x gradient, there is the same phase twist that's applied on the magnetization of our voxel, of our pixel that's happening. So the relative phase of this relative to this is the relative phase of this to this, but this twist here is due to the position in y, due to the application of the gradient along y. We'll do the next step. So we have twice the gradient amplitude along y, so the phase is twice as big here to start with. We'll just draw the 7 time points along x, and as we apply the gradient along x, then the magnetization develops along x as we see here. We'll do the third step, and we'll have the phase evolution during the y gradient. Now for each of the n steps, the gradient that's applied here is proportional to delta gy, so it increases linearly with time. If we go in the opposite direction, we'll have the starting phase of the magnetization in the opposite direction, twice the opposite direction, and 3 times the opposite direction, again with the phase being twisted by the readout gradient. So here we had no evolution along x, so we see the starting phase of the magnetization for each of the gradient applications along y. Here was no gradient application along y. Here we have the pure effect of the x gradient. Now, the question here is, does the computer who will digitize this 7x7 matrix here, will the computer be able to distinguish whether these 7 points have been recorded sequentially or these 7 points have been recorded sequentially? Look at the magnetization vector here and the magnetization vector here, and you will see that this particular column and this particular row, they are, in terms of magnetization vector, they are indistinguishable. We cannot distinguish their positions. So, from a standpoint of computer, and the computer is a stupid machine, at least those computers that we are talking about here, it does not know how the data was acquired. It just gets the data. If it now examines this data set, it will not be able to say from this 7x7 matrix, we've been encoding these 7 time points sequentially, or we have been encoding these 7 time points sequentially. So in essence, when you store the data in the computer in this fashion, then the way the data is stored is the role of phase encode and readout gradient are interchangeable. They can no longer be distinguished. And so the phase encoding amounts essentially to frequency encoding, which is what we're doing in the x direction, in the same way. And this comes from the simple fact that if we have a change in phase with time, like here, this corresponds to a precessional frequency that we have seen. That's very simple. But if we now introduce to the second dimension also a time component, then this phase evolution here will also correspond to a frequency, a precessional frequency, except that it's not real time, it is the time variable introduced by phase encode steps 1, 2, 3, etc. So if we look at the signal of the voxel we have here, we can attribute this to a delta time delta t, so we can introduce along y a second time component. Or in general, our signal is given by the nth gradient, phase encode gradient n, the increment of the phase encode gradient delta gy, which is constant. This is proportional to the transverse magnetization at the beginning at the position x and y. That's this particular xy. This is the effect of the phase encode gradient, so it's gamma n times delta gy is this amplitude gy, and e to the I gamma gx times x times t, that's the evolution during the readout gradient. Again, here we have not considered echo formation. We are assuming we're starting at the echo. The principle here is more important than exact detail. So this is our signal of the individual voxel. And now I will introduce the definition of two variables, kx, that's gamma gxt, and ky, which is gamma gy tau. These are the phases, the phase terms proportional to the phase terms. With these definitions, we can rewrite our signal as a function of kx and ky. We have the transverse magnetization, that's this term, and now the phase term here changes, and you can verify this gives us the kx times x plus ky times y times I. That's our signal of our voxel with this transformation of the variables. Here, this is what we relate to the experiment, but these are mathematical variable transformations. Okay, so far this is the signal for a single pixel, pointwise object. How about the signal for an entire object? Well, we're going to have to integrate along x and y, so we'll do a two-dimensional integral across our object in x and y. Our signal along at the kx, ky is proportional to the transverse magnetization at that position times e to the I kxx plus kyy. Well, what does this resemble? Maybe you've come across similar expressions already. Well, this is the Fourier transformation of the object. Or, to obtain the MR image, we have to do the Fourier transformation of the signal. Remember, this is the signal we record. This is with the variable transformation. We have a Fourier representation. To get this from this, we have to do the Fourier transformation, so we get the magnetization by doing the Fourier transformation of the signal here in k-space. So k-space and real space, that's like Fourier space, and real space, it's like reciprocal space, that's the k-space, the term. Here x and y are the real space, but the image, the process of acquiring the image with MRI, essentially what we are acquiring is the Fourier transformation of the object. And to obtain from the data that's stored in a computer, to obtain the image, what one has to do is a two-dimensional Fourier transformation.